see if we can get this all set up. If you didn't make copies of that, that is perfectly fine. I'm going to make this a little bit bigger for myself. So again, I am not looking at all at the Zoom right now. So again, you're going to need to speak up if something does come up about that. I'm going to have to get mommy out of here. All right. So endothermic, exothermic processes. It's been a while since we've discussed these, but hopefully you remember there are two things that exist. The system and the surroundings, where the system is exactly what you're studying. The biggest problem that people have with this is the beaker, the thermometer, and stuff like that. Those are the surroundings. It could even be the water, right? That's the biggest one. Usually we determine the change in temperature of the water or the solution. If the water and the thermometer is showing that it's getting colder, that's a surrounding, so that means that the system is actually doing what? You can jump in if you want, but I'm going to maybe give 2 seconds or whatnot. The system must be gaining energy. Why? Because the thermometer is within, it's a surrounding part, even though it's touching the system or it's relating to the system. If it's getting colder, the system is gaining energy. That's a big one. That's a hard one for us to see a lot of the times. If the thermometer is getting warmer, then it's the opposite. The system is losing energy. We've talked about this before. We said it's important to define the system versus the surroundings. I always give the example of a piece of ice within my hand. I say, is that endothermic or exothermic? And then you would question whether or not we're looking at the piece of ice or my hand, because you can't have an endothermic without an exothermic occurring. It all depends on what you define the system as. So energy of the system equals negative energy of the surroundings. One is gaining, one is losing. Now, heat for us is basically a property that transfers from hotter objects to colder objects. Enthalpy is basically the change in heat. Now, enthalpy a lot of times is delta H. That's showing us it's a change. Heat is sometimes just called Q. So that's the amount of energy that is transferred. The change is going to be delta H, or the enthalpy. Q does not necessarily need a sign. Enthalpy needs a sign. You can say how much heat is lost, and you wouldn't put a negative there if you were just talking about Q. You would just say this amount of heat is lost. It wouldn't make sense to say negative heat is lost. It would make sense to say the change in enthalpy, or the enthalpy is negative or positive. This will always have a sign, but if we're just talking about heat and you're saying absorbed or lost, you don't need a sign necessarily for that. Work comes more into play with physics, but the definition of work in physics is a force exerted over a distance. Force over distance. Even if you're like holding up, like we were just talking about somebody in a weights class, if you were just holding up a weight, I believe that's called an isotonic exercise. If you were just holding up a weight, your arms may get tired. Maybe isometric. I can't remember the difference between the two. But if you were holding up a weight, your arms may get tired. But since it's not being exerted over any distance, you're not truly doing work in the scientific form, right? The force being exerted over the distance is going to be that work. So even though we may have a job and it seems like we worked hard, we may not have worked as hard in the scientific aspect. Now, with this work, a lot of times there's two things with energy, a lot of times with science. We have heat and we have work being done. That's the basic things. A lot of times we look at a combustion engine like moving a car. There's work being done with the pistons moving and the tires spinning, but a lot of the actual energy from the thermochemical reaction of the gasoline burning is lost due to heat. There we go. Heat, amount of thermal energy transferred from something hotter to colder. You cannot give something coldness. You can only take heat away from it by basically having something colder near it. So you can't give something coldness. It has to lose its heat to something else. The unit for heat are joules, kilojoules, or calories, or kilocalories if you're going into nutrition or something like that. If thermal energy is lost, then delta H is going to be negative. If thermal energy is gained, then delta H is going to be positive. And here is where work is. Work is the energy needed to move something. Again, as we said, a force exerted over distance. In chemistry, we think about expanding gases that push on things. Again, that's going to be that combustion engine and the pistons. Now, for chemistry, this is a little bit weird. We look at the system as the gas. If the gas expands and pushes on a piston, that's our negative work. The system has done something to, the system has done something to the surroundings. If we have the surroundings push on the system, then that's going to be positive work. And that allows us to add work and heat energy together if we were determining the enthalpy, like the change in these things. Work is equal to negative P times delta V. If we were to do this, force is newtons, and distance would be meters, so that would be Newton meters. That's what physics use for work. If we do this with what we call R units, work is equal to negative P times delta V. That's going to be meters cubed, and pressure would be atmospheres. And we can basically multiply these through using this liter atmospheres to get 101.325 joules, and we're going to be able to cancel out the units here to end up with Newton meters. And I can show you that. I don't want to spend a lot of time on that today, but I can show you that more in detail. Or if you watch the film from, help me out, from the schedule for today, that will definitely be in there. This one doesn't go as much into detail as that, and we kind of determined at the beginning why. It's because this work formula is not on the sheet. You probably just need to know this conceptually. If the system is pushing on the surroundings, the work is negative because the system is basically putting work on, it's giving off that force over that area or that pressure over that volume, and that's going to be negative. If we're pushing or compressing on the system, then that work is going to be positive. No. The rest of this is basically review. We've seen these guys before. So, again, I'm not watching the chat, so if you have any questions, make sure you do make them vocal or have somebody make them vocal. But an endothermic process, here we start down low, we end up higher. The enthalpy is positive, or the delta H is positive. The products have more energy than the reactants. If we looked at it like this, we looked at the little man diagram plus the money, and then this would be the man with the money, right? So the amount of heat or the amount of money here is greater. This would be the man with the money, and then the man separate from the money means that it's lost it. This is that enthalpy being negative. A lot of times when you're dealing with this, I think it's said right here, whenever we talk about a change in temperature, it might be a little bit later then. There are also other ways that we can see this without a change in temperature. The biggest one is heat equaling mc delta T. If you recall, that's the MCAT equation. Mass, specific heat capacity, change in temperature. The other one is your delta H of like fusion or vaporization or anything like that. That's a change in state. Well, guess what doesn't happen during a change in state? No change in temperature. So that change in temperature will not be in that formula. Instead, it will be based off of mass or moles. And then you will have this delta H, and basically you just do, wouldn't be stoichiometry unless you had a balanced equation, but basically just dimensional analysis. So if we take a look here, let's see if I can zoom in here. Whoop. Phase changes do not have a change in temperature. So on here we see these flat plateaus. That's where it's vaporizing. Here's where it's melting. This is a process of heating ice. Remember, the ice itself can be lower than 0. We have to heat it up to 0, and then we can, come on, dude. And then we can actually, yes, say hi. No. Then we can actually get the particles to start to separate. Solids will be in a crystalline form, whereas liquids will be able to freely move around each other. And gases, whenever you get up to here, the gases will be whenever the distance between them is much greater than the size of the particles themselves. These are called heating curves. These are called energy diagrams. Remember, this is reaction progress versus potential energy. You could also do this, it wouldn't be the same, but this is kind of the version of that whenever it comes to changing the state. Remember, what we're starting with here is the same chemically as we're ending up here. It's the actual particle diagrams that would change. Here they would be very close together. Here they would be very far apart. Student of the month question. Why is this so much bigger than this? Yeah, somebody will have to talk for student of the month today, if they want it. Nice and loud.
I'm sorry. I'm guessing because the intermolecular forces are stronger at that point?
Look at that. You even used a good word. The intermolecular forces that need to be combated here are greater, right? We have that hydrogen bonding here to break that crystalline pattern. It doesn't take as much energy to break that hydrogen bonding and have those particles actually fly away from each other. That takes a lot more energy. That's an FRQ question easily. The opposite process, again, we're going to do this. Now take a look. If we don't worry about the supercooling part right now, but if we take a look at this and this, those amount of energy per mass are going to be the same, right? So the energy that needs to be added to vaporize is the amount of energy that needs to be lost to condense. And the same thing here. Somebody give me a time, please.
I think we have 4 minutes left.
All right.
Yeah,
So we're only going to get to, it looks like, the first one. That's fine. When a solution forms, there are 3 processes that take. This is one of those, again, FRQ all day long here. Remember, it takes energy to break things. Yeah. Normally, we're talking about breaking the bonds in the reactants, and then whenever those bonds reform, energy is released. Again, I'm not going to fight Mr. Sue on that. It is the breaking and reforming of the bonds that allows energy to be released. Here's the big thing for this. If you drop particles into water, the solution forms, the same thing happens. The solvent must expand by overcoming its intermolecular forces, the solvent in this case being water. It takes energy, as we talked about when Bree said, it takes energy to break these intermolecular forces, right? That's endothermic. That means energy is required to break those. The solute must then have its intermolecular forces broken as well, right? So that's also an endothermic process. In the end, whenever the solute gets in between these particles and they recombine, that's exothermic. If these parts take more energy than is released, then that's going to be an endothermic process overall. If these parts take less energy than is released, then in the end, that solution is going to feel warm to the touch, and that's going to be exothermic. If it releases more than the energy that it takes to break both of these things. That's a big thing. Think about that, a few times today if you can. That's a hard concept to get by. We know hot packs that exist that show this. They are exothermic because they heat up the surroundings. And we know cold packs where the chemical reaction exists where they actually require more energy and they bring that in. Instant coffee, if you look up here, freezing liquid to solid is exothermic. Sublimation, solid to gas, is endothermic. If the particles get further away, then they are gaining energy. If the particles get closer together or stop moving entirely, they are losing energy. Talk yourself through that a little bit. And then for the assignment, if you guys would, just finish up this page 3. And that should be good. And you have until Friday for that. This is the first one of, what do we call non-mastery points? Not participation points, that's what I want to call them. But this is the first one of those. Remember, those do count in the end. Questions? Hopefully that doesn't feel too fast for you. Most of this was review. Big things to take away. This right here, read through that a few times. The other one is this new work thing. And if you're in physics, that may be a little bit weird for you. The other thing is a big thing right now is people that are freeze drying things. I don't get it, but basically you're doing two things. You're lowering the temperature, and then you're vaporizing off the water as it's freezing. I do have some freeze dried Skittles. We'll bring, hopefully, if we meet tomorrow in class, I'll have those for you guys, and you can try them out. I'm not a huge fan, but some people like them. That's all I got. Have a great day, guys. Thanks for joining me.
See ya.
See ya.
Bye. Bye.
Bye. Thank you.
Thank you.